Hello friends, in previous lecture we see a definition of linear differential equation and its solution which contain complementary function as well as particular integral. So in this lecture we see how to find out a complementary function for this. So here we discuss about complementary function which is shortly denoted by CF of linear differential equation. To find it first, we find auxiliary equation by substituting d by dx is equal to capital D, which is differential operator, and equate it to 0. We get algebraic equation in terms of d. After finding the roots of it, we easily reach to complementary function. There are 4 cases to find out complementary function. We see one by one here. In this slide we see first case, if the roots are real and distinct. Here we have to take, if we have a linear differential equation of order 5, then we get algebraic equation of order 5, and so we get a 5 roots. If all these are real and distinct, like a1 not equal to a2 up to not equal to a5, then complementary function is equal to c1 e raised to power a1x plus c2 e raised to power a2x up to c5 e raised to power a5x. If the roots are real and repeated, we see again linear differential equation of order 5. Again we get a algebraic equation of order 5, so we get a 5 roots. But in this case 2 roots are equal and the remaining 3 are distinct, like this. a1 is equal to a2, which is not equal to a3, not equal to a4, which is not equal to a5. Then complementary function is equal to c1 plus c2 x e raised to power a1x plus c3 e raised to power a3x plus c4 e raised to power a4x plus c5 e raised to power a5x. In the next case, if the roots are complex and distinct, suppose we have to take linear differential equation of order 4 and we get algebraic equation of order 4, so we get a 4 roots obviously. If they are all complex and distinct, means a1 plus minus ib1 not equal to a2 plus minus ib2, both are complex, not repeated, means distinct, then complementary function is c1 cos b1x plus c2 sin b1x whole bracket into e raised to power a1x plus c3 cos b2x plus c4 sin b2x into e raised to power a2x, where the imaginary part comes with trigonometric and real part comes with exponential function. Similarly, we see if the roots are complex and repeated, again we have to take a linear differential equation of order 4. We get algebraic equation of order 4, and so we get a 4 roots. If they are complex and repeated, that is a1 plus minus ib1, which is equal to a2 plus minus ib2, then complementary function become like this: c1 plus c2x into cos of b1x plus c3 plus c4x into sin of b1x whole bracket into e raised to power a1x. For getting this case clearly, we see some example on it. But before starting the example, we note here, if the function f of x is equal to 0 in linear differential equation, then complementary function become a solution of it. So first example we see, solve d2y by dx square plus 4dy by dx plus 4y which is equal to 0. So we substitute here d by dx is equal to capital D. So we reduce this given differential equation in this form, which is nothing but d2 plus 4d plus 4 whole bracket into y which is equal to 0. After equating this algebraic equation in terms of d to 0, we get auxiliary equation, which is d2 plus 4d plus 4 which is equal to 0. After finding the factor, we get d plus 2 into d plus 2 which is equal to 0. So we get d is equal to minus 2 minus 2 times. So the second case is occur. Here we get a real and repeated roots. Therefore complementary function is equal to c1 plus c2x e raised to power minus 2x. Since f of x is equal to 0, so obviously CF directly become a solution here. In the next example, we see d2y by dx square minus 9y which is equal to 0. So clearly we get auxiliary equation is d2 minus 9 which is equal to 0. So it implies that d2 is equal to plus 9, and therefore d is equal to plus minus 3. Since we get real and distinct root, means first case is occur, therefore complementary function becomes c1 e raised to power minus 3x plus c2 e raised to power 3x, and therefore again f of x is equal to 0, therefore complementary function directly become a solution here. In the next example we see d2y by dx square plus 16y which is equal to 0, so obviously auxiliary equation become d2 plus 16 which is equal to 0. So after shifting this 16 on the right hand side, obviously we'll get d square is equal to minus 16. Here we have to write down d square. Therefore d become plus minus 4i, and since these are complex roots where the real part is 0 and imaginary part is plus minus 4, so therefore we have to write down complementary function by using the third case, which is c1 cos 4x plus c2 sin 4x into e raised to power 0x, but e raised to power 0 is equal to 1, therefore we get a solution like this. Thank you.